I think that I can introduce Xavier Cabré by a metaphor. I cannot find any other words. I think he's the Big Bang of more or less of the activities today and tomorrow. In the early times of the Big Bang, I think was his teaching of PDAs in the faculty, the works that have been mentioned by Joaquin with Solar Morales and so on. But then it came an inflation time, which is the PhD thesis of Xavier Ross and Joaquin Serra. And I believe, or it seems to me, that today we are in the discovery of the gravitational waves that are allowing us to see the early times of the universe and proving something, okay? So, I believe that his talk goes very far away to conjectures of a long time ago. It's a work of the four people, Alessio, Xavier, and the other Xavier, Joaquin, and I think this is very, very fitting to finish the lectures today.
Thank you, Sebastián, for the... Can you hear me well? Thanks for the introduction. It's a pleasure to be here. It's a pleasure to have Alessio listening to the talk. I'll check that you don't do your math. Maybe it's not for me to say, but if I was in another situation, I would be a little... I'm usually confident when I have to give talks, but I would be a little worried or scared because of the previous talks, right? The level of the previous talks, and I'm not sure if it will be at the level. I'm sincere, but since, for instance, two of them were from my students, I'm very happy about that, and I'm just happy. If it's not at the level, no problem. Another day, maybe it will be better. It was not so simple to prepare because it's very technical, and but I hope it will turn out to be okay, and the audience also is not specialized. I'm going to speak about a result that I work for, a conjecture that I worked for 23 years, I think, 96, beginning of 96, when I got my second postdoc in Paris, so 23, and that we solved with Alessio, Joaquim, and Xavier well, the paper was finished last July, and you find it in archive, okay? So I will explain the story maybe a little more detail later on. To start, I want to do just basics, that something that I think all here, all students can understand and see a little, at least understand something of the problems, eh? Because proofs are rather technical. Just a little bit at the end about proofs. So here we have the Laplacian, or minus the Laplacian, is a second order linear operator for acting on functions of n real variables. So x is a point in a domain in Rn, right? This is the Laplacian. And first fact in linear PDEs, but this already gives you some work. It's not so easy, but it's basic for us, is that the Laplacian is an isomorphism between two Banach spaces. There could be other choices, but I chose these Banach spaces, which are called Holder spaces. Here, C2 alpha means that I have a function that is twice the differentiable, and the second derivatives, partial derivatives, are Holder continuous with an exponent alpha. Alpha always between 0 and 1, strictly between 0 and 1. And here I have to consider functions that vanish on the boundary. Then if you take a function like this and you make two derivatives, for sure you will get into this space continuous functions which are more than continuous, Holder continuous with an exponent alpha, so that the Laplacian maps x into y is just trivial, it's just the definition. But the important point is that it's an isomorphism. If you give me a function here in C alpha, there exists a unique function u u in the space X, so it is a C2 alpha function in the bounded domain. This is a nice, smooth bounded domain that vanishes on the boundary. It's important to put this condition. And then you have uniqueness. And therefore, it's a solution of this problem. We write it like this in PDEs. It's Laplacian, it's G, and it's 0 on the boundary. So this is a boundary value problem in PDEs that we call the Dirichlet problem. And it's well posed. It has existence and uniqueness. And not only existence and uniqueness, it's an isomorphism in the functional analysis meaning, which means that it's not only bijective, but it is continuous, and the inverse is continuous. And being continuous and the inverse being continuous means two inequalities. So at the end, in PDEs or in analysis, everything reduces, no, not everything, but many things reduce to inequalities, right? This is the trivial one that I pointed before, and this is work. This is work, this is linear work, that is the Schauder theory that appeared in the talk of Xavi, applied to then to nonlinear problems after linearizing them, right, in some way. But here we are linear. By the way, do you know what happens if you put alpha equals, one would like to put alpha equals 0. Is the Laplacian, because it would be a simpler space, right, the ones that we teach in calculus 2, is the Laplacian an isomorphism between C2 and C0? It could be, but it is not. It is not. So, so it's very important that alpha is bigger than 0. All right. So Holder spaces are very, very important. So let's go now to my nonlinear problem and the nonlinear problem that our joint paper deals with. This is the problem. It's still functions that are 0 on the boundary, and and that now solve the minus Laplacian of u equals a nonlinearity that only depends on u. There are no derivatives here, but f is what we call the nonlinearity is a function from R to R, say, and lambda is a real parameter. This is called a reaction diffusion problem. Diffusion is the Laplacian. It's related with Brownian motion, and this is like a reaction term, a right-hand side, and these models like this appear in many situations in phase transitions and competition between two species, in cosmology, many in fluids, rotational, incompressible fluids. Also, you have PDEs like this. So it's a quite basic equation, or one of the most basic equations in nonlinear elliptic PDEs. So let's take f of 0 positive. You can think of f of u equals the exponential of u. It will be an important example. F of u equals the exponential of u. If f of 0 is positive, then the trivial solution, u equals 0, is a solution only for lambda equals 0. If you take lambda equals 0, 0 is the solution. But 0 is only the only solution, is a solution only for lambda equals 0, because f of 0 is not 0. So now you can ask yourselves, are there solutions for other lambdas, non-zero? And of course, what the first thing you do is to think of basic calculus and the implicit function theorem. We are going to solve the problem for lambda at least small enough, around 0, through the implicit function theorem. And that's easy, right? From the previous transparency, I set up the nonlinear problem from this Banach space, C2 alpha, functions that vanish on the boundary, the reals, and then y was C alpha. And the function psi is just the equation that I want to solve. I want to solve this equals 0. So I want to solve psi equals 0. Of course, u equals 0 and lambda equals 0 is a solution. And through the implicit function theorem, I want to find u as a function of lambda for lambda small enough, right? And if I want to find u as a function of lambda, what I have to see is if the functional really depends on u. If the functional depends on u, after linearizing it, I will be able to invert to find the solution. So what I have to do is the linearization with respect to u. Okay, so I perturb, like Joachim did in his talk, say, in Joachim it was u plus t phi, right? Here I will call it u plus epsilon psi. And I write it like this, and now I collect terms without epsilon, terms with epsilon, and terms with epsilon square. It's very simple. And this will be the linearization acting on psi, on a perturbation psi, the linearization of my original problem. Laplace is linear, nothing changes. This is nonlinear, I have to differentiate it. With respect to u, it's just putting instead of f of u, f prime of u, and then multiplication by psi. So this is an operator. Now I go back to my point u equals 0, lambda equals 0. This zero order term disappears because lambda is equal to 0. I get the Laplacian. It's an isomorphism. The implicit function theorem tells me for small lambda, you can find a unique solution of the problem around 0, small solution, and you can write it like this, u as a function of lambda, right? The nonlinear problem has a Lagrangian or energy behind. This is funny that I didn't talk to you, but in your slide also you use Lagrangian and energy. So this shows that there is consistency between students and advisors, which is good. And I put energy in quoted because in PDEs we call it energy. But in real classical mechanics, say, or calculus of variations, you should call it the Lagrangian, right? And as in Joachim talk, it's like the Allen-Kahn energy that he presented, Dirichlet energy that toda la vida. And then potential energy. But in my problems, I will not have this. I will not have this double well potential. But keep thinking of the model problem I told you. Small f being the exponential of u, capital F the primitive. Capital F is a primitive. Also the exponential of u. So I will have lambda times exponential of v. This is the Lagrangian or energy. You do the first variation, the Euler-Lagrange equation. I can do it now faster because you already saw how to do that in Joachim's talk. And you will find the Euler-Lagrange equations. Critical points of the energy will solve my PDE. Do it very fast, just perturb, write everything, just perturb, make the derivative with respect to epsilon. This is quadratic, it becomes linear. This is nonlinear, it stays nonlinear. I put epsilon equals 0. I get this expression. So quadratic, bilinear, zero order term. I integrate by parts, like he did. And I leave psi here alone. This integral must be 0 for every psi. This guy here must be 0. And you get the Euler-Lagrange equation. This is the first variation. And now I care about the second variation of energy. Because I'm going to be interested in these states which are stable. We'll come to it later, but now it's much easier for me because Joachim already made the job. But let me try to explain a little. Well, the second variation of energy, I have to differentiate this still again with respect to epsilon and put epsilon equals 0. And I find the linearized operator, by the way, that we had already found here, because here I had, this was the first variation of energy, and I'm making one more variation. So this is the first variation of the Euler-Lagrange equation, is the second variation of the energy. So I'm redoing everything again, but I'm doing it on purpose because when I compute like in this way, I find the linearized operator, but I find it after integration. I find the quadratic form. Or I find, if you want, the linearized operator that I found using the implicit function theorem applied to psi, but here it appears after doing a scalar product in the Lebesgue space L2. Let me put again u equals 0, lambda equals 0 as in the implicit function theorem. Well, this part here disappears, or this part here disappears, and I get a quadratic form, which is grad psi square, which is non-negative. So from this other way, more energetic, I realized that the Laplace is not only an isomorphism, but also it's a positive operator. If psi is not 0, this will not be 0. Psi equals constant is not allowed because psi has to be 0 on the boundary. So the only constant is 0. So I learned that minus Laplace, it's a positive operator. In fact, minus Laplace, it has an infinite number of eigenvalues that go to plus infinity, and they are all positive, right? They are all positive. Well, this is a theorem of PDEs, and functional analysis. So a solution of my equation is said to be stable if the linearized operator is non-negative definite as operator. If you want, you can check it in this way. Do the quadratic form, which is an integral for every xi in the space x vanishing on the boundary. This quantity is greater or equal than 0. This is the linearization of the prime, but it's the second variation of energy. Being non-negative, it exactly means what Joaquin was describing, that I have a critical point which is like a local minimum of the energy. And I wrote it in other ways, but similar to what Joaquin said. Well, stable solutions correspond to critical points of the energy which are local minima, more or less, philosophically speaking. And I wrote these are observable solutions, or solutions that persist under small perturbations. And that's why the catenoid, when stable, still doesn't break, right? You perturb a little, and you are still there. Or you could think of a dynamical system. So take the equation and add ut minus Laplace u equals f of u. So at time, this is a nonlinear heat equation, and it becomes an evolution problem like a dynamical system. If you have a critical point which is a minimum of an energy, and this energy is like a Lyapunov function or something that decreases with time, then it is going to be stable in the sense if you perturb a little, the dynamical system brings you back to the minimum. All right. So stationary. Stable solutions are stationary solutions that are limits as time goes to infinity of nonlinear heat flows after, for instance, after perturbing a little the initial datum, okay, which is the stationary solution. Our paper, by the way, it's about stable solutions of this problem, and that's why I had to define this. Let's continue. I'm not happy enough with the implicit function theorem. Well, I can use the global implicit function theorem, right? That says, like a global version or a continuity version that says, okay, this branch, as long as the linearized operator at the solution that I found with the implicit function theorem stays positive, as it was in the beginning, that was minus Laplace, it will stay positive for some time by continuity. As long as it stays positive, the branch will be continued through the implicit function theorem. So you continue like that, but you realize that the linearization is the linearized operator is very dangerous because it is here, and it will have minus Laplace minus lambda f prime of u. Let's think of the exponential. This is the linearized operator. Okay, this is positive, but a lambda, if lambda gets larger and larger, this guy may beat this positive because it's subtracting. So at some point something may happen, right? So let me get an idea of what can happen from a variational point of view. Well, the energy, it's infinite. It's difficult to understand the energy because Okay, at u lambda it will have a local minimum, but then this there is a minus here, and this is exponentially growing, so the energy for sure will go down. All right, will go down, and in fact, my space where the energy is defined is infinite dimensional, so not so easy to treat, right? But let me get an idea just drawing the energy on lines, like what we did with the perturbations, on lines. Let's fix a function v. So here I'm not proving anything. It's just to give me some hints of what can happen. But I cannot prove anything like this. I must be infinite dimensional. But let me be for a second finite dimensional and draw the energy on the ray along a function. So you just fix a function and now take a real parameter t and write the energy. Well, this becomes a function of one real variable. We all know about one functions of one real variable. This is a polynomial, t squared, then there is the minus, there is a parameter, and there is something that behaves like the exponential of t. So now I can draw exactly the shape of this energy in time for when the variable is t. For lambda equals 0 is a parabola. This parabola should stay locally for lambda small. So for lambda small, there is still a parabola, but the origin is no longer a critical point. It has negative derivative. So the new solution is not 0. It has to go to minus infinity. So something has to be produced here. It looks like a local maximum, but I'm not sure because this is in infinite dimensions, right? And then you realize also that when lambda is sufficiently large, the derivative of this with respect to time will always be negative, always negative. So no critical point. Behind this, there is a theorem of okay. So this problem was studied or proposed by Gelfand, and there is a joint paper or note or survey Barenblatt of Barenblatt on the Gelfand problem. The Gelfand problem is when f of u is equals exponential of u. For more general nonlinearities, we'll call it Gelfand type problem. It's a problem that comes from a model, say, in combustion theorem, when you put the exponential of u. And well, we will work always with this set, or most of the time with this set of hypotheses on the nonlinearity, like the exponential here, f of 0 positive, f increasing, convex, superlinear at plus infinity. This is one of the models, and this is the power model. These ones are also okay. 1 plus u to the power p, p bigger than 1. Increasing, convex, and superlinear at infinity. And now here I will consider lambda positive, say. It is not, this was proved by a group of people, say. So, and it's not so difficult to prove this. It says, start from here, please, which is simpler. If lambda is bigger than a certain parameter lambda star, there are no solutions. That's what it was indicating my last drawing in the previous slide, all right? And this parameter lambda star, we call it the extremal parameter. After, there are no solutions. Before, for lambda between 0 and lambda star, there is a stable classical solution. For every lambda, there is at least one stable classical solution. In fact, there is at most one. Being stable, there is a unique stable. It's the one that I found with the implicit function theorem in the beginning. And in fact, I could get them all with implicit function theorem. The branch is increasing with lambda. So these are functions that are increasing. And as lambda goes to lambda star, they increase to a function that now, well, what does it mean, classical solution? Classical solution, I mean, for instance, C2 alpha. In that space, C2 alpha, in the space X. The limit is a pointwise limit. So the limiting function maybe is not C2 alpha. It's not uniform convergence, say. It's just convergence in L1. I'm able to prove convergence in L1 and get an L1 function that is distributional stable solution of the extremal problem. The extremal problem is when lambda equals lambda star. This solution, U star, we call it the extremal solution of the problem. Then 8 years later, more or less, 9 years later, Joseph van Landeren made the first, systematic study, more detailed study of the problem for the exponential nonlinearity in the radial case. In the radial case, the PDE becomes an ODE because the radial case means that you are the domain is a ball and the functions are radially symmetric. So at the end, the function only depends on the radius. So the Laplace operator becomes an ODE, second order ODE, that you can start a study with ODE techniques, phase plane analysis, whatever you want. And what they found is this picture, that up to dimension 9, they found the branch of stable solutions. It's this branch. At the extremal parameter, they found a classical solution. And then the branch continued, because here the operator was positive, positive. Here the operator becomes to have a first eigenvalue, which is 0. And bifurcation theory tells you this branch has to continue, but to the left. And then they found that it goes to the left and then starts spiraling like this around another parameter lambda here that I don't care about now. And for dimension 10 and higher, instead the solution, the branch, as lambda goes to lambda star, blow up in L infinity norm. So this weak distributional solution, U star, the extremal solution, they could see that it was unbounded in the unit ball and for the exponential. I want to show you, but these were only ODE techniques. I want to show you a way to understand, to tell you who is U star and to understand more from a PDE point of view why in this dimension U star is unbounded, and tell you who is this guy U star. And this was done by Brezis and Juan Luis Vázquez in a paper that will come up later, a very important paper in this business. To explain you that, to tell you who is this guy, I need to present you an important inequality in PDEs, which is called the Hardy's inequality, that answers this question. When is this operator non-negative definite or positive in a domain of Rn? The operator is minus Laplace minus a constant divided by the distance to the origin to the power 2. This is a special operator. Why it's a special operator? It has some nice property. Because if you rescale space, if you pass from meters to inches or yards or whatever, this rescales like minus 2, because these are two derivatives, so meters to the minus 2. And this other term also rescales like meters to the minus 2. So this tells you that there is some invariance under rescalings for this operator, and therefore there can be some interesting inequality behind this operator. And in fact it is. It is the Hardy's inequality, and tells you whatever is the domain containing the origin, there is this inequality which is true for every function with compact support in the domain. You need the dimension to be greater or equal than 3. And the inequality says the Dirichlet norm of da tutta la vida controls the function in some way. So functions controlled by derivatives, right? This is very common in PDEs. But now in this case, I have the same exponent on both sides, and I have this potential here, 1 over x squared. And here there is a constant. And the proposition also says this is the best constant in the inequality. You cannot put bigger constant. This is the best one, and the inequality is true with this one. So this gives an answer to this question. This operator will be non-negative definite if and only if the constant is not too large. It has to be less or equal than the Hardy, what we call the Hardy constant. Okay. What did I want to say about this? Okay, when you see an inequality like this, you have to check that it makes sense. For instance, the function psi equals 1 cannot be here, because if you had constants, this would be 0 for constants, and this is not 0, so this is not true. That's why I'm putting 0 boundary values. The function must have 0 boundary values or must have compact support somewhere. All right? And then the idea behind these inequalities, like the Sobolev inequalities, the gradients of the function, the derivatives of the functions, are able to control the function itself. The function cannot be too large if the derivatives are under control. Okay? It's like the mean value theorem, but more sophisticated. But still, this one is the only one that I can prove for you in one line. Then there are these Sobolev inequalities and are much more sophisticated, but they look similar. But this one can prove in one line. Let me just give you the idea, but very fast. This seems to be complicated, but it's not so complicated if you use spherical coordinates. You write x as r times sigma, and r is the radius to the origin, the distance to the origin, and sigma are the angles, so sigma are in the unit sphere, and r is the radius. This could be, in this I can suppose that I'm in all Rn because I extend the function, since it has compact support, I extend it by 0 outside. So it's the same in all Rn, and I'm writing in all Rn, and this is here I put the Jacobian. You know, in spherical coordinates, the Jacobian is r to the power n minus 1, but I have another minus 2, so n minus 3. And now this is the trick, very simple. You write r to the n minus 3 as the derivative of r to the n minus 2, and you integrate by parts. And when you integrate by parts, the rn minus 2 remains here, and you have to differentiate psi square. And you get 2 psi, derivative of psi with respect to the radius, which is part of the gradient of psi. And now you see, oh, now I'm fine, because I will do Cauchy's worse with the blues, will give me this, and the reds will give me back to this square root, and I'm finished. Well, one has to do the details, but it's very simple. In general, in PDEs, these type of inequalities are not so simple, okay? But this one is nice and it's important. So now here it is. You try now for functions, radial functions, that could solve this nonlinear problem. You try a little. You try powers. Doesn't work. Well, you try a logarithm. I'm trying singular solutions. So now I go back to we are back to the question that appeared in the talk of Xavi. Are solutions bounded? Is the extremal solution bounded, or it's unbounded? Here I'm studying the extremal solution, which is the limit of stable solutions, and therefore it's stable. So I'm mixing the two talks of them. Are stable solutions regular or not regular, right? Well, you try, and then like somebody was saying yesterday, I don't know if Xavier or Joaquim, it's very useful to have, okay, right? Or this morning, this morning. Sometimes it's very useful to have, and this can be useful to everybody, to have like an explicit solution of maybe a particular case of the problem that you are working with. If you have a very general problem, if you have for a particular case an explicit solution, it can be very useful and can be used as a guide. For instance, this happened very strongly in my paper with Joan Sola Morales that Joaquim mentioned. And so you try, and here you try another one, singular one, very, very, very standard, which is a logarithmic singularity. And then you can compute the Laplace. It's just an ODE. You compute the Laplace, derivative with respect to R, two derivatives. Well, you compute, and you are lucky, and you see that it solves the Gelfand problem with parameter lambda equals 2 times n minus 2. Whoa, I found a singular solution. And now I wonder, is it observable or not? Is it stable, or is these ones that we don't see in nature because it's unstable? Well, you do the linearized operator. This is linear minus Laplace. The derivative of the exponential is the exponential itself, but the exponential of u is 1 over x squared. Here it is. The exponential of u for this solution is 1 over x squared. So this is a Hardy type operator. Is it going to be positive? It will be positive definite if and only if this constant, 2 times n minus 2, is less or equal than the Hardy constant from the previous transparency. And this means that n is greater or equal than 10. So this singular solution, logarithmic singularity, is stable in dimensions 10 and higher. And that's why it can be limit of the branch of stable solutions, classical stable solutions. In less dimensions, it cannot be here because it would be stable, but it is not stable in dimension 9, 8. And this so beautiful synthetic short analysis was first made by Jaime Bresis and Juan Luis Vázquez that I know. So, and again, we see the thing that Xavi told us this morning, that in high dimensions, there are more chances to have singular solutions and less in small dimensions. Okay. So after this, the questions is now, okay, this is a particular case. It's the exponential nonlinearity, and for the unit ball, what if I have another nonlinearity? What if I have another domain and my PDE is not an ODE because it's not radial? Solutions are not radially symmetric. So these are the questions. When are stable solutions, when is the extremal solution bounded? And therefore, once it's bounded, again, like in Xavi's talk, once I'm able to prove that the extremal solution is bounded, by linear methods, I'm able to prove that it's C2 alpha, C infinity even. So the point here is to prove if it's bounded or not. Because once it's bounded, f of u, the reaction term, which is the danger, is also bounded. So the right-hand side is bounded. The Laplace being bounded is a very strong thing, and I get more regularity. So this is written for the extremal solution, or I could state it more generally, like Joachim, like when are stable solutions of this type of equations bounded? This is what I wrote here. This is the energy space, the Sobolev space, but I'm not talking about Sobolev space. So when are stable solutions bounded? Let's write it like this. This is the PDE analog of the problem that Joachim mentioned. That is the regularity of stable minimal surfaces in Rn. This is a very important open problem in differential geometry, very difficult. Many people would kill for proving this. I think, geometers mainly, but also analysts, right? Why not? When are stable minimal surfaces, those ones that we saw in the photographs of Joachim, regular or not? It is known that this is not true in dimension 8 and higher, and it is known that it's true in dimension 3, but this is already 40 years ago. And it's open. It's open in these dimensions. It's like a little embarrassing, but it should not be embarrassing. It is a very difficult problem, but hopefully it will be solved at some point. For minimizing minimal surfaces, it is known that they are regular up to dimension 7, as Joachim said. So it's something that we know how to prove for minimizers. For stable, is much tougher. All right. And here we are saying the same. We are seeing like the dimension, instead of being 8 or 7, the cut dimension 7, 8, in our case should be 9, 10. But at this point, 72, it was only known for this nonlinearity and this domain. So now let me tell you the story. The first result after Joseph Langren is by Crandall Rabinovich, some years later, 75. And they prove a nice result. The extremal solution is bounded, or every stable solution will be bounded. I'm writing all this for the extremal solution, which was the motivating problem. But the answers at the end say energy stable solutions are bounded if, what did they prove? If the dimension is less or equal than 9 and the nonlinearity is very close to the exponential or a power. Very, very, very close. In particular, if it's the exponential or a power, but also they could deal with nonlinearities which are quite close to them. Second derivatives also close in a way. It's a very nice result, and this in every domain. So we are out of the ODE radially symmetric setting. For this I'm very happy, but still the nonlinearities are particular ones. But that's good. Then, well, 75, 85, 95, 22 years later, 21, it's when I arrived to Paris, and Bresis was very interested in this problem because of some progress they had made for the parabolic version, for the evolution version. And he put many people to work on it, say. Juan Luis, one of them, myself, I got very much interested, and some students of him. They have some papers where they state the conjectures or the open problems. The one with Juan Luis, there are like 8 or 9 open questions. Then Bresis wrote another one by himself, and these are some of the questions. Is the extremal solution always in the Sobolev space, H1, the energy space? Well, let's focus more on this. Bresis wrote, is there something sacred about dimension 10? Is it possible to construct a singular stable solution for n less or equal than 10 in some domain and for some nonlinearity? Is it possible or it's not possible? At that point, we didn't know very much what would be true. A student of Bresis proved that regularity holds up to dimension 3. Very nice result, in fact. It's something. And this for every nonlinearity of the type increasing, convex, superlinear at infinity. So it's good enough. Think of these nonlinearities: increasing, convex, superlinear at infinity. And this was a nice paper of a student of Bresis. It was his thesis. Let's forget now about this other thing, since I don't have so much time. And then I had a paper with a PhD student of me, Antonio Capella, at that time, and we proved that in the radial case, regularity holds up to the optimal dimension 9 for every nonlinearity. This was for absolutely every nonlinearity. It is at this point when I start thinking that the conjecture should be true, that the answer to this question should be no. It is not possible to construct stable solutions up to dimension 9 which are singular, because in the radial case it's not possible. And if it's not possible in the radial case, I have hope that it is not possible in any domain. So from this point on, I would call it the conjecture of Bresis. So this was a good progress. And then the most important one I did some years later. This is a CPAM paper, nice paper. And I could go up to dimension 4. An interior, very nice interior bound, and up to the boundary if the domain was convex. Just keep that I could go up to dimension 4 with very, 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 very nice estimate, L infinity estimate. This is 2010, okay? Well, Salvador Villegas in Granada extended nicely some of my results, made some extension, very nice extension. I don't have time, I'm sorry. Then with Xavier, Rosoton, we could go up to dimension 7 for domains that we call of double revolution. You split your n variables into groups, and all this part is radially symmetric, and all the other part is radially symmetric. So they are domains of double revolution. It's not an ODE anymore, and we could get up to two more, up to dimension 7. At that point, I thought, this problem is very difficult. I believe on it. I'm not pessimistic, but I need to speak to other people because it's just like this. And then I spoke to somebody who liked it a lot and who is very strong, one of the strongest PDEs in the 20th century, Joel Sprague, who is still in Baltimore, who is still doing very good job, very good work. We tried, but we didn't succeed. It was not, we could go up to dimension 5, but with an assumption on the nonlinearity that we were. That's not the point. The point is to try to prove it for every nonlinearity. Okay. And then this is our paper that you can find in archive, our result. It says, first it's an interior estimate. Up to dimension 9, you have a beautiful L infinity and also Holder continuity estimate. First in the interior, this is how the paper starts, like often in regularity theory. And then the boundary regularity. Here you see global regularity. If you have a stable solution, no matter what the nonlinearity is, up to dimension 9, you have the estimate, and solutions at the end will be C alpha, and therefore C infinity if you want. Here there is only one assumption on the nonlinearity. For the interior regularity, the nonlinearity must be non-negative. For the regularity up to the boundary, we need more. We need F to be non-negative, F increasing, and F convex. The corollary is that the extremal solution is always in the energy space in every dimension, and it is bounded up to dimension 9. We have results in dimension 10 and higher, but are not L infinity estimates because they do not hold in these dimensions. Can I have like 2 or 3 minutes? 2 or 3? Okay. Let me just give you a very fast idea of how the proofs work, just to give a flavor. They are quite technical. The first thing is to try to find a guy that solves something interesting for the linearized operator. Here in red is what is the linearized operator, and you see it when you write, this is the stability condition. I have two informations, the stability condition and the PD that says minus Laplace of u equals lambda, or here forget about the lambda, f of u. I have this, and I have the stability condition, which is this. It is important to write the stability condition for psi being the product of two functions where C will play a key role. You have to choose C in the right way to satisfy something nice for the linearized operator in red here. So let me tell you how C or how psi was chosen through the history of the paper. Of the problem. Crandall, Rabinovich, and Nedev didn't do this trick of writing psi as C times zeta. They directly worked with psi that was a function of u. No derivatives, just a new function of u, and tried to find h appropriately, depending on f, to get some interesting information. And this could, and Nedev made it work up to dimension 3. And Crandall-Rabinovich up to dimension 9, but for nonlinearities very close to the exponential or to powers. Okay, so something else was needed. Well, the radial case was great to do the radial case, because here it's first time when it appeared this decomposition, and the important thing was to choose in the correct way C, as pretty much C is UR, the radial derivative of U. If U satisfies this PDE, the radial derivative, if I differentiate with respect to the radial derivative, here I will get f prime of U, UR. It's like the linearized operator, and here I have to commute the radial derivative and the Laplace, and I cannot commute it. There will be an extra term. So I can expect the radial derivative to satisfy something interesting for the linearized operator. And this is the case. Unfortunately, it gives the optimal result, regularity up to dimension 9. And the other part of the test function psi, the eta, it's very natural to find it with this proof as a power of the distance to the origin. So this, at the end, this is the test function in the radial case. I don't know why in the non-radial case for a while I didn't know what to do with this. And some years later, I could do the dimension 4 case with a very different test function that was the modulus of the gradient, and this is the key choice of C. Then after this, well, 2010, it's all these years that there was no important progress. But I kept working on it. Then, like in 2000, before you graduated, like 2013, perhaps, I made quite a big progress. I made a quite big progress, and I told my student first only to try to keep it here, right? And get the result here, but we were not able. I mean, it was a very important progress that was almost solving the problem, but we could not get the L infinity estimate. It was frustrating, but we could not. And we could not. And then I decided to go around the world and talk to some people, selected people that I could trust and that I thought that they were strong on these things. And I won't say names, but there were like 4 or 5 people, and we didn't succeed. But I persevered, say. And then 3 years ago, 3.5, well, yeah, three and a half, I went to Zurich, and I explained the problem to Alessio. And he got very interested by it, right? Captivated, say. And for a week, we worked together. I mean, I didn't force him. I didn't force him. But he would come to my office almost every day. And okay, we realized some things, but we could not solve it. And that's like 3 years ago. And then 1 year ago, I went to Zurich for a conference that Joaquim, Xavier, and Alessio organized, beautiful conference at the ETH. So I was there for the week of the conference, and I stayed 1 more week. And I was stubborn, and I said, please, could you, Alessio, Xavier, and Joaquim, come all together to my office on Monday, or Tuesday, maybe Monday, I'm not sure. Doesn't matter. Because you all know this problem, and if we add force, right, and inputs, there will be more chances. And I think already the first day we felt good. We went back, we went to lunch or whatever, feeling good. You were there, Matteo. You have to think that I had worked on this problem for 23 years, right? So, but we were feeling good, but no big deal, say. On Tuesday, we started feeling better, right? And then after 3 days, we could see that we were getting very close, or we almost had it. And then I remember having my plane probably on Friday, and in the afternoon, and sitting on a table just to go faster, sitting on a table next to Alessio. They had to go to teach, sitting with Alessio to make some details, right? Technical details that we were quite convinced that they should be okay, but we want to check, and then Alessio, impressive Alessio, took his speed to check the details, and I had to say, okay, I have to go to the airport, but everything is fine. So I went very, very happy. So for all this, thanks Alessio, thanks Joaquim, thanks Xavi, because you all contributed very importantly, and it makes a lot of sense that you are Doctor Honoris Causa for the UPC, I think, at least from my point of view. So thanks for your attention. By the way, in our paper, we need to use both Cs. that one that seemed to be the good one, but I didn't know how to use here. We use it, and it's the first one we use, and it's very, very important. But then at the end, we also need this one. And these are what they satisfied for the linearized equation. Sorry.
This is a good comment. So, are there more comments or questions?
Oh, yes, yes, yes. Yeah, I'm forgetting something. If somebody wants to ask me something that I should be saying? Well, Matteo promised that that there was something after the figalata, right? That I learned from Alessio during lunch, that figalata, for a Spaniard or a Catalan, when we understand figalata, it's funny, right? And sounds like figali, figalata, like something coming, something nice, something strong coming from figali. But in Italian, figata, figo is something beautiful, bonito, figo. And figata is una cosa bonita. And so when an Italian says figalata, it means figali, but something very, very bonito, right? Nice. And then the day we solved this, or one of the days we solved this, then we went for lunch, very happy, I think, quite happy. And then I said, Alessio, I'm going to change name. I mean, you contribute so much solving this problem. It's so good. I'm going to change your name. Let's see if you like it or not. Instead of Figali, I will call you Filzgali. And that was kind of funny also. Of course, at that point, you had not won the Fields medal yet. Yeah, just Just? This was right after the film. Sure. Well, it would have been nicer even if I called you before, like saying, okay, it was right after.
Extra wisdom.
Yes.
Well, so thank you very much.
Sure. Thanks for the attention.
Thank you all for attendance, and thank you the speakers, and many thanks Alessio for coming. It's been really a pleasure to have all of you here. Really interesting, all the talks, and I have enjoyed very much. Thank you to all. Thank you.